In this lecture, we are going to talk about improper integrals of type 2. So improper integrals type 2. So what are improper integrals of type 2? So the situation is like this. So we can say, let's look at these two graphs. So there's a graph like let's say 1 over x. So this is at 1, so the function takes 1. So the problem is like if you want to find the area under the curve, so this is y equal 1 over x curve. So what we try to do, we try to find the area below the curve from 0 to 1. So the corresponding integral would be, so it is 0 to 1 over x dx. But you can see that now there's a problem. So what's going to happen when you have 1 over x, and you can see that when x reaches 0, at 0 the function is not defined. So see, at 0 function not defined, so you're going to get a vertical asymptote so of the curve. You can see that it's going to go to infinity when x reaches 0. So when x reaches 0, you can see that the function goes to infinity. Okay, that's one situation. Let's also look at, so the question is, what is this area below the curve, whether it's a finite number or not. And also a situation like this, so it's a very similar curve, but at this time what's going to happen, so it is like this little closer and then go like that. So so you can see this is y equal 1 over square root x. So I slightly change it, so it is not 1 over x anymore, it is 1 over square root x. And again we can ask the same question, what is the area below the curve of this part. So that means the corresponding integral would be 0 to 1 over square root x dx. And so what's going to happen, actually for our surprise, we can see that this integral you're going to get a finite number, and here it is infinity. So so you can see that that's very strange. We slightly change the problem, but you're going to get completely different answers. So so what we're going to notice in this situation is the function, so the function becomes infinite. Function becomes infinite. Function become infinite at one of the endpoint, at least. Okay, it can be both, but at least. So function becomes infinite at the one of the endpoint. That's one of the observations that we have. And then you can see that in these situations you're going to see vertical asymptotes. So there are vertical asymptotes. So there are vertical asymptotes. So there are vertical asymptotes in this situation. So there are vertical asymptotes. So those are the kind of, and then so in this situation the result is not obvious. So so the area can be finite or infinite or finite. So it's not obvious situation. So there are, so anything can happen. It can be finite or infinite. So so what we do next is we'll try to look at the corresponding definition, and from the definition then we're going to do like some problems there. So let's look at the definition. So as before, we can have we have three cases. So the definition, the first one, let's say if the function fx is continuous on the interval a to b. So at a it is open, b close, and discontinuous and discontinuous, discontinuous at a, discontinuous at a. So the function is continuous from 0 to a, but it is discontinuous at the point a. So like that. So it is it's continuous from a to b, but it discontinuous at point a. So that's the situation. Then what we can do when we write the integral like this, then you write the definition, then the meaning of a to b is what? So meaning of a to b fx dx is simply, so you can take the limit. What we're gonna do, we're gonna pick a point in the inside the interval, so I'm gonna call it c, and then what we do, we're gonna send c to a from right. So that's how we do. So we pick a c inside, and then we're gonna send c to a plus. So we're gonna integrate from c to b in this case, and then we have fx dx. So that's what we have. So what we can do, so we pick a c, and then we integrate from c to b, and then we send c to a from right. So that's the first case. So let's look at the second case. So the second situation, so it's very similar. So we have if fx is continuous on a to b and discontinuous at b now, the upper limit. Then what we can do, it's again a similar situation. So we have so this a to b open now, a to b. So now what we can do, as before, we're gonna pick a c. So we're gonna pick a c, that's a c, and then what we do, we're gonna send c to b from left. We're gonna send c to b from left. Okay. So it is a to b fx dx is limit. What we can do, we're gonna pick a c, but c you send to b from left. So it is now a to c fx dx. So that's the second case. So you can see that in the first one you have a discontinuity at a, in the second one you have a discontinuity at b. Now the third case, there's a discontinuity in the middle of the integral somewhere. Okay, so inside the integral, so inside the interval. So if we can say fx is discontinuous at c, and c is in between a and b, it's not equal to any of them, but it's in between, then what's gonna happen, what we're gonna do, we're gonna split the integral from, so we have a, b, so there's a c somewhere, but we're gonna split the integral from a to c and c to b, and then those two integrals become either case 1 or case 2. So we're gonna go back to those cases and solve. So what we do in this case, we're gonna split the integral. So we have a to b fx dx. Now there is a discontinuity in the middle of the integral. What we do, we're gonna split the integral from a to c fx dx plus, and then c to b fx dx, c to b fx dx, and you can see that in this situation, so the first one is there's a discontinuity at the upper corner, that's the second case, and here there's a discontinuity in the lower limit, so that's the first case. So what we do, we're gonna solve those two separately. If at least one of them is infinite, we're gonna say it is discontinuous. If both are finite, we're gonna say it is it's integral converge. So converge and diverge. If at least one of them is infinite, we say the whole integral diverge. If both are finite, then we're gonna say the whole integral is converge. So So we can say if the limit exists, we say integral converges, otherwise diverges. So what we say, if the limit exists, if the limit exists, we say the integral converge. If the limit does not exist, we say it's diverge. And then what's going to happen in the last case, if at least one of the integral diverges, we say the integral diverges in part 3. Okay, so the part 3 is different. So there are two integrals. We're going to check whether at least one of them is diverge. So if at least one of them diverge, we say the whole integral diverge. So now what we need to do is, let's look at several examples and see how it's gonna go. So the first example, test whether the integral 0 to 1 over square root x dx converge or diverge. Okay, converge or diverge. So we can check whether it's converge or diverge. So what we can do, again as before, there are 3 steps here. We're going to apply the limit definition, integrate, find the limit. So let's go in that direction. So the answer, so we have the integral, which is 0 to 1 over square root x dx. So what we're going to do, we're going to write the limit definition. That's step 1, limit definition. So it's a limit. So what we have here, we have open at 0, close at 1. Why open at 0? Because at 0 it does not exist. So so we're going to pick a c here, and then we send that to 0 from right. So 0 plus. So it's a limit. C goes to 0 plus c to 1 over square root x dx. So that's what happened. That's the limit definition. Now you can see that. So why we do that? You can see. So there is a discontinuity. There is a discontinuity. There is a discontinuity at x equal 0. That's why we're gonna do at the lower limit. So we always do that at the place where there's a discontinuity. Okay. So and then what's gonna happen? So we can finish it. So it's a limit. C goes to 0 plus. We can integrate this one. This is a very easy integral. So we can do c to 1. This is x to the negative 1/2 dx. And then you can finish the integral. So it is c goes to 0 plus. So you're going to get x 1/2 divided by 1/2, and then you're going to evaluate at 1 and c. So you're going to get limit c goes to 0 plus to square root x 1, and I'm just adding extra steps here. And then limit c goes to 0 plus. So that's step 2. So we're integrating it. So let's plug in the values. So you're going to plug in the value. So when you plug in the value, you're going to get 2 when you plug in 1 and minus 2 square root c. Now what we want to do is find the limit when c goes to 0. When c goes to 0, you know that this term goes to 0. So that means your answer becomes 2. as it becomes 2, but we know that this is a finite number. It's less, so that's how we write it, finite. So it is finite. So we can say, so the integral 0 to 1 over square root x dx converges. So that is the kind of situation, and you can see that it's not that difficult. You just need to follow the steps. So this is the actually third step where you find the limit. Okay. So let's do more examples. So the example number 2. So how about this one? So evaluate 0 to 3 1 over x minus 1 dx. 0 to 1 over x minus 1 dx. So, and if you look at the graph of this function, so how it looks like. So it is like so at 1 there is a discontinuity, or there's a vertical asymptote. At 1 there's a vertical asymptote, so that's 1. So the graph gonna go like that, and then graph gonna go like this. So this is y equal 1 over x minus 1. So you can see that there is a, so this graph gonna go to infinity on this way, this gonna go to negative infinity on that way. So so there is a discontinuity. There is a discontinuity at x equal 1. So there's a discontinuity at x equal 1. So that means what we're gonna do, that's inside the interval. So the interval go from 0 to 3. So what we're gonna do, we have to split the integral. So what we're gonna do, we're gonna consider two separate integrals, and if at least one of them is infinite, you know that you don't want to do the other one. That's enough. So what we do, let's split the integral first. So we can write this one 0 to 3 1 over x minus 1 dx. So so this is equal, since the discontinuity, we can split this at 1. So we can go 0 to 1 1 over x minus 1 dx plus 1 to 3 1 over x minus 1 dx. So what we can do, we can do one of them, but normally what we do is we do the easy one, but if you can figure out which one is easy, just do one of them. So 0 to 1. So let's do the first one. So what we can do, we're gonna go from the left. So we're gonna go from, so we pick a number and then we're gonna go from left. So so we can do that. So that means your integral, it is 0 to 1 over x minus 1 dx, because you can see that there is discontinuity as 1. So but we do the first one. So that means we do write this one as a limit. C goes to 1 minus 0 to c 1 over x minus 1 dx. And then what's gonna happen, so that's the limit, and then we're gonna integrate this first. So it's a limit, c goes to 1 minus, we know that this is a simple integral, this is ln x minus 1, that's the integral, and then we can evaluate this one at c and 0. So let's plug in the two values. So it's a limit, c goes to 1 minus, so we're gonna plug in c first. So it's ln c minus 1, and then minus ln negative 1 absolute value, but negative 1 absolute is 1, so that means this simply becomes ln 1, so which is 0. So you only have the limit, c goes to 1 minus ln c minus 1, and then you can see that when c goes to 1 minus, so c goes to 1, that's a c, this is 1, c goes to 1 from the left side, what's going to happen, c minus 1 goes to 0, c minus 1 goes to 0. So if c minus 1 goes to 0, what will happen? Ln. So we can look at the graph of natural log. So in the graph of natural log, we know that if this number goes to 0, and then function goes to negative infinity. So negative infinity, that means this is going to go to negative infinity. So this limit is infinite. So so you can see that this limit is infinite. This limit is infinite, so the integral diverges. So the integral diverges. So if one integral diverges, you don't want to do the other one. So so you only need to do one of them. So if you figure out that at least one of them diverges, you can stop right there. The reason is if one diverges, the whole integral diverges according to the definition. So you only need to do one of them. Okay. Now how about let's say, so I'm going to write this as a warning. I'm going to say not. So let's say by mistake we did not know that there was a discontinuity, and we simply can integrate. So 0 to 3 1 over x minus 1 dx. Let's say we forgot about that, there's a discontinuity. So you're gonna get natural log x minus 1 3 and a 0. So what you do, you're gonna plug in that. So if you plug in 3, you're gonna get ln 2 minus. If you plug in 0, you're gonna get ln negative 1. Ln negative 1 absolute value, but which is 1. So you're gonna get ln 2 minus 0. So that means this is ln 2. You can see that you get a completely wrong answer. So so I should say that this answer is wrong. This answer is wrong. Okay, this answer is wrong. So you want to make sure that when you have this kind of integrals, whether there are discontinuities. If there is a discontinuity, you want to split the integral at the discontinuity, and then you want to consider those two integrals separately. So you want to make sure that this is right. So let's look at another example just to exaggerate the point. So the next example, let's say evaluate 0 1 1 over x minus 2. So you get a problem like that. So you can see that in this integral there is a discontinuity at 2, but that 2 is outside of the interval. So what we can notice is that so there is no discontinuity on the interval 0 to 1. So that means this is just a regular problem. So what's going to happen, 0 to 1 1 over x minus 2 dx. So this is a proper integral, it's not an improper integral. So you can so actually if I graph this, so that this is the situation. So you have 2 and 0 and 1 here, and then the 2 is outside. So you can see that the 2 is outside, but your actual in a definition of the integral is this, so it's outside, so that means you don't want to worry about that. Okay, so in this case you can just basically do the integral. So it is ln x minus 2, and then we're gonna evaluate the function at 1 and 0. So if you do that, you're gonna get ln, if you plug in 1, you're gonna get -1 absolute value, minus, if you plug in 0, you're gonna get -2 absolute value. So this is gonna be ln 1 minus ln 2, but you know that ln 1 is 0. So what's gonna happen is so you're gonna get -2. This is a -2 ln 2. If you bring the -2 inside, it is ln 1/2, and then you can see that this is finite. Okay, so finite. So it's just a basic integral. So there are no issues with this. Okay, so I'm going to give you a problem for you to try. So how about this one? Just extra credit problem. Converge or diverge. Converge or diverge. Okay, converge or diverge. So let's say 0 to 3 x over x minus 1, and then x minus 2 dx. So you can do that just to practice how to do it. Okay, so let's do one more problem of slightly different type. So this is the last example of this type. So how about this problem? So example, so evaluate. So let's do 0 to 3 dx over x minus 1 2/3. Okay, this integral. So you can see that there is a discontinuity at 1. So there is a discontinuity. There is a discontinuity at x equal 1. So what we can do, we have to split the integral at 1 as before. So so you can write the integral as 0 to 3 dx x minus 1 2/3. So what we're going to split the integral at 1. So it is 0 to 1 dx x minus 1 2/3 plus 1 to 3 dx x minus 1 2/3. Now what we can do, we can use the definition, and so let's consider the first integral. So if you consider the first integral, consider the first integral. So we can write this one as 0 1 dx over x minus 1 2/3, but you know that there's a discontinuity at 1. So there's a discontinuity at 1. So the integral is from 0 to 1, but there's a discontinuity open. So what we're going to do, we're going to pick a point here and send that to 1 from left. Okay, so it's a limit. C goes to 1 from left, 0 to c, 1 over x minus 1 2/3. This is a very easy integral. You can bring it to the top and add. So so you can write this one as limit c goes to 1 minus. So if you write this one as 0 to c x minus 1 negative 2/3, this is very easy to integrate. So you add 1, it's become 1/3, and divide by 1/3 means multiply by 3. So you're going to get limit c goes to 1 minus 3 x minus 1 1/3, and evaluated at c and 0. So let's plug in the two numbers. So it's a limit c goes to 1 minus, if you plug in c, it is 3 c minus 1 1/3 minus, if you plug in 0, it is 3, you're gonna get negative 1 1/3. Negative 1 1/3 means negative 1, because negative 1 multiply 3 times by itself, you get negative 1. So if you take the cube root, you still get negative 1. So that means this is simply negative 1. Okay, so that means this all become 3. So it is 3, the last part is 3, and then we have plus the limit c goes to 1 minus 3 c minus 1 1/3. So let's try to understand this now. So what's going to happen? So that's a 1. So you try to go from this, because it's going to go for 1 minus. So that's a c. So c try to go to 1. So that means it's all less than, c is less than 1, but getting closer. That means the inside part is getting closer to 0. So right, so this part is getting closer to this is getting closer to 0. So c minus 1 goes to 0. So that means this whole integral simply goes to 0. So this limit is simply 0. So that means your final answer is 3, and which is finite. So that means as this is finite, that means the integral converge. So this part of the integral converge. So that means the integral from 0 to 1 dx x minus 1 2/3 converges. That's another way to write converges. So since that one integral converge, now what do you want to do? You have to do the other one as well. If one diverge, you don't want to do the other one. But if one converge, you want to do the other one, because we don't know whether the next one is converging or not. So we have to do the other one as well. So that's the argument. So let's do the next one as well. So we're going to consider the next one. So you can see here what's going to happen. This is 3 and this is 1. You have to go to this way, so it's a 1 plus. So you pick a c, but c go to 1 plus. So that means your new integral become 1 to 3 1 over x minus 1 2/3 dx. So here the discontinuity is at 1. So that's where you're going to see the discontinuity. So that means you want to write the limit for that. So it's a limit c goes to 1 from plus. You go through large values. That's a 1 plus. And then the limit. So and then we integrate. So it is c to 3 1 over x minus 1 2/3. The integral is very similar to the last one. So it's a limit c goes to 1 plus. So it was 3 and then what happened, c minus 1 1/3. Okay, c minus 1 no, actually 3 minus 1. So it is not c. So when you plug in so let's write the integral. So x is x minus 1/3, and then we plug in the value 3 and c, and then so it's a limit c goes to 1 plus. So let's plug in the values. So and then what's going to happen if you plug in 3? So it's become 2. It's become 3 times 2 to the 1/3 minus. Here you get 3 c minus 1 1/3 Now we're going to consider what's going to happen here. As before, when c goes to close to 1, so here the first one is we have 3 cube root of 2, thus we have, and then minus this one become 3, the limit c goes to 1 plus c minus 1 1/3, and you know that this limit is simply 0 as before, so you simply end up getting 3 to cube root. That's what you get, but you can see that this before is finite, so that means this integral also converges. So that means 1 to 3 x minus 1 2/3 dx is also converging. So that means the total integral converge, because this converge, so that means the total converge integral. So so therefore you can say 0 to 3 1 over x minus 1 2/3 is dx is simply the sum of the two, 0 to 1 1 over x minus 1 2/3 dx plus 1 to 3 1 over x minus 1 2 over 3 dx, and then you can see that the answer is the sum of the two. The answer is sum of the two. So one you get is 3 for the first one, the second one was 3 cube root of 2. So if you simplify this one, you can take 3 out, 1 plus 2 square root, no, that's not right. So it's a so you're gonna get 1 plus cube root of 2. Okay, so that's the answer. That's the answer. Good, but you can see that we kind of don't know until we kind of split the integral, because if you just by mistake did not worry about the discontinuity, and if you try to integrate a 0 to 3, sometimes you get the answer, sometimes you do not get the answer. For example, in the last case we do not get the answer, but here actually you can see that you're gonna get the answer. So yeah, so there is a problem. So so what you need to do is, when you have discontinuity, make sure that you split the integral at the corner. Make sure that you split the integral at the discontinuity and consider two separate integrals and integrate them separately. If one converge, then you have to converge the other one also. If one diverge, you don't want to do the other one, because if one diverge, the whole integral diverges. Okay, so this is the end of section, end of the type 2 improper integrals.